So welcome to the Warren Seminar by Dr. Mark Board and the dedication of the Lacabanne Rock Mechanics Laboratory. My name is Joe Labas. I have the privilege of serving as department head. There are a few items of business I'd like to get clear. There will be some words about Dr. Lackabon. I will then invite Charles to also provide some remembrances. Dr. Board will present a seminar, and at the end, we will have a dedication that starts in this room with our guests on Zoom, and then we'll conclude in the Rock Mechanics Lab with a brief dedication to Dr. Lackabon. So with that, certainly we're here to honor the past, and we have a number of distinguished alumni, faculty, friends, but I also would like to acknowledge our present faculty and students and staff. So thank you so much for everything you do for the department and, of course, for the geoengineering program. A special thank you to Emmanuel. So Emmanuel and I worked very hard in contacting a number of you for the remodeling of the Rock Mechanics Lab. And you've been incredibly generous. And again, Emmanuel, thank you so much. I'd like to acknowledge our graphic artists. So you will be seeing in the presentation that I'll be giving some of the work of Nick Neary, our graphic artist, and of course, Emmanuel and I worked with Nick. Okay, with that, what I'd like to do is read some remembrances from Dr. Lackabon. The first one is provided by Professor Emeritus Paul Weiblin, a very good friend of Dr. Lackabon. And there will be three personal notes that I'll interject in this text. Washington David Lackabon was born in 1903 in San Francisco. His parents were French immigrants. So the first note, I would sometimes see Dr. Lackabon reading a textbook or novel written in French. When Dave was about 6 years old, his mother applied for citizenship. The presiding judge asked, "What are the names of the handsome boys beside you and the child you're holding in your arms?" When she replied, "Washington David Lackabon and Lincoln Lackabon," the judge said, "Madam, you are a citizen. I have no more questions." When Dave was in high school, he built a cat whisker radio. This was not only an early indication of his engineering talents, but it also led to a summer job as the radio man on a San Francisco, Alaska salmon fishing boat. His fellow crew members called him Sparks. Dave earned his bachelor's degree in electrical engineering at the University of California, Berkeley, and his PhD in petroleum engineering at the University of Minnesota. During World War II, Dave taught an introductory physics course in the university's college training program. As a lab exercise, he had the students build a generator in the student shop. Dave was a private person, but we know that he raised two sons, Leon and Andre, as a widower. Upon retirement in 1972, Dave continued his research work in the Department of Civil and Mineral Engineering. His routine was to come to the university at 7 a.m. and leave at 3 p.m. As Dave passed my office in Pillsbury Hall, I could set my watch to 3:05 p.m. Note 2, on my first day at the university in September of 1987, I walked into my rock mechanics lab and was promptly kicked out by Dr. Lackabon. The 84-year-old professor was tiling the floor. During Dave's retirement years, Professor Gus Bitsianis and I would take him to breakfast on Saturday mornings to the town talk on Lake Street. Dave would regale us with stories of his life in California. When we asked him why he left California to come to Minnesota's cold winters, he said, to get away from the cold, damp nights in San Francisco. There was nothing colder. We learned that Dave was an accomplished ballroom dancer. He spent Saturday evenings at the Prom Ballroom on University Avenue in St. Paul. His lady friend's son befriended Dave in his later years. Note 3. I believe it was 1996. Dr. Lackabon fell while putting on his boots, and he was hospitalized for several days. He tried to get back into his 3 a.m. to 3 p.m. routine, but he could not. He was not the same Dr. Lackabon. Gus Bitsianis, Dave's sons, and I helped Dave move into the Catholic Elder Care Nursing Home in Northeast Minneapolis. He quickly became involved in the activities of the home, among other things, teaching ballroom dancing in their physical therapy program. Dr. Lackabon passed away in 1999. Thank you, Paul. And now a remembrance from Michael Vogel, former student. I encountered Dr. Lackabon for the first time in Min E 113, Introduction to Petroleum Engineering. Imagine, if you will, a time so long ago that a university course only needed 3 digits. This was a time when an electrical analog computer was being used to solve Laplace's equation in applications related to flat seam mining. The model was first developed in South Africa, and Dr. Lackabon was charged with building a similar analog computer here. A number of students provided the labor, and the work was conducted in his petroleum engineering laboratory. I was one of the students that worked for Dr. Lackabon constructing the electrical resistance network. I spent many hours working closely with him, soldering resistors and modifying the design. For example, we added automated data acquisition. It seemed he was never at a loss to come up with a clever solution. Of particular note is that our analog had a resistance network that simulated an infinite field, making the entire front face usable. One Sunday morning, I was completing work on one of the outermost layers. I noticed that geometrically, the resistors in the outermost layer did not follow the resistance patterns I had observed. I brought this to Dr. Lackabon's attention, and he did not seem too pleased with me. So I went back to soldering. It was actually a pleasant surprise when he came back into the lab and said, "Michael, you're right." My memory here is one of mutual respect. And I expect many other students felt the same way, given the effort he expended helping all the students. I probably ought to mention the help he gave the rock mechanics graduate students. A particular memory is the rock mechanics toolboxes. Each toolbox had tools that were correspondingly numbered, and woe to the assignee that was caught with an incorrect number in their assigned toolbox. And double woe if a tool in the box happened to have the petroleum engineering triple color stripe. Dr. Lackabon was a generous man of many talents, which he graciously shared with students. I not only considered him a friend, I believed he was invaluable in implementing the practical aspects of the numerous field and laboratory research projects undertaken is the rock mechanics program developed at the University of Minnesota. Thank you, Michael. It is now my honor to introduce Professor Emeritus Charles Fairhurst. Of course, Charles needs no introduction, but I will simply state that through the leadership of Charles, the University of Minnesota became one of the leading research centers in rock mechanics. Please join me in welcoming Charles.
Well, thank you, Joe, for the invitation. It's a pleasure to be here. About a decade ago, I was in a group of friends, and I noticed a little girl about 3 to 4 years old holding her mother's hand and looking at me with a very quizzical look on her face. I smiled at her, and she looked back and said, "How old are you?" "I'm 83, I replied. "No, you're not," she answered. I said, "Why do you say that?" She said, "Nobody's ever that old." I'm now about 10 years older, and I'm still here. But it put me in mind of a comment by Dr. Lackabon soon after I met him. When I arrived here in 1956, I was 27. He was about 53. "You probably look in the mirror every morning," he said to me. "One day you'll see an old man." I'm not sure what he was replying, but I think, because he's very private, but I think he was telling me, time is fleeting. Make the most of your opportunities. It was also during that first year that he came to me and said, "Do you have any plans for Thanksgiving?" Well, to be honest, I wasn't even sure what Thanksgiving was. So he said, "I'd be pleased if you would join me and the family for dinner." It was there I met his wife and 2 sons, Leon and Andre. We had a pleasant meal, but what followed was totally unexpected. Each of the 4 took up a string instrument. His wife may have played the piano, actually, and I think Dave played the cello. They entertained me with classical pieces for the rest of the evening. He then took me home. I shall never forget it, but he never discussed it afterwards. That was the kind of private person that he was. He was teaching petroleum engineering, but he still volunteered to help me. He was invaluable when in 1957 we organized a student trip to an underground iron mine in Crosby, Minnesota, to carry out a mine ventilation field exercise. From then on, he became the de facto supervisor of the rock mechanics lab as we embarked on studies of the mechanical behavior of rock. The lab to be dedicated today is actually part of the 3rd building on campus in which I had the privilege to work with Dave. First, Appleby Hall, the original School of Mines, then the School of Mineral and Metallurgical Engineering is now the western part of Chemical Engineering Materials Science, and since 1981 here. Although long retired, Dave would still come to the lab every day. He was in charge and was still there when I retired in 1995. Dave's involvement with the rock mechanics lab during and subsequent to Wolfgang Wawrzyck's pioneering work on stiff testing machines deserves special note. There were quite a few students in the lab. It was in the basement of the building that's now part of CMS. And the first MTS machine was potentially dangerous for the uninitiated. Dave took this responsibility very seriously, and woe to the student that did not listen. It was this period that led actually to a close interaction with MTS and to the MTS professorship, which has brought and continues to bring many distinguished international visitors to the department and its students, and close bonds with our faculty. Take note when you go in there also of the rock scratcher device, a remarkable development by Drs. de Tournay and Drescher that can provide much of the rock property information with a simple, non-destructive test on the rock core. There's much more that I would love to talk about, but I must stop. Thank you, Dr. Lackabon. You will never be forgotten by your colleagues and your students. And now, future students will be reminded of you also. This is a very fitting tribute to a wonderful and very dear colleague. Thank you.
Thank you so much, Charles. It is now my privilege to introduce our Warren Seminar speaker. Dr. Mark Board has worked as a mining consultant on every continent for more than 40 years. His single goal is to introduce safer and more economical mining methods based on sound rock mechanics principles. Mark earned all his degrees, bachelor, master's, and PhD in geoengineering at the University of Minnesota. After his bachelor's degree, he worked in various phases of the mining industry, both in the US and internationally, before completing his PhD requirements in 1994 with Steve Crouch as his advisor. Mark was part of the Itasca Consulting Group for over 20 years, and he recently retired, or semi-retired, in May 2020 as Vice President of Technical Services for Hecla Mines in Coeur d'Alene, Idaho. I now will mention only a few of his many honors. Mark's PhD dissertation was awarded the Rocha Medal of the International Society for Rock Mechanics in 1995. This international medal has been awarded annually since 1980 for the best PhD dissertation in rock mechanics. The award to Mark is the only time in the history of the ISRM that the Rocha Medal has been awarded to an American citizen. In 2012, Mark received the prestigious Rock Mechanics Award of the Society of Mining, Metallurgy, and Exploration. This is awarded to recognize the most outstanding person internationally in rock mechanics. In 2014, Mark received the Outstanding Alumni Achievement Award from the University of Minnesota. Also in 2014, Mark was elected member of the U.S. National Academy of Engineering for contributions to the design of large-scale mines based on application of advanced rock mechanics principles. Please join me in welcoming Mark Board.
I thought I would start off with just a couple of thoughts about Dr. Lackabon because I actually worked with him in the lab. And in I think it was probably 1972 or 3, I first came into the department here and I was given a job by Professor Crouch, and it was to work and help the PhD students in the lab prepare their rock samples and things like that. And he told me, go down to the lab, Dr. Lackabon will straighten you out and show you the ropes. And so I'm not going to repeat his lab rules here, but this is more or less what he told me at the time. But the thing I did want to mention is that he reminded me so much of my father. It was amazing. My dad even kind of looked like Dr. Lackabon. And when we came into the lab, the first thing which Mike Vogel has already mentioned is that he had a real fondness for tools, and he had painted on those tools so that we knew whose tools they were. They didn't get lost. And he, of course, gave me all the rules about what to do with the tools. And it reminded me of my dad so much because in our garage at home, he had a giant pegboard, and he outlined every tool on that pegboard in ascending length, like all the wrenches started, the small ones got bigger. And my dad painted the handles red. And I remember asking him, he said, so I know if somebody takes a tool, where it is and and where that tool went. And so I immediately got to enjoy Dr. Lackabon a lot. He was kind of a stern guy at first, but he was just one of the nicest people that you'd ever meet, I think. And I wanted to point out one thing, and that is this thing right here, which I understand will be down in the lab when you go there that you can have a look at it. It was an ingenious little device that he made that was a mini stiff and soft testing machine that you could polish the ends of pieces of chalk and put it in there. And by taking these springs and removing them and just having the load bear, you turned a handle down to compress the sample. But you could either put those springs in series with the load or outside the load, so it would store that energy up. And when that sample failed, if you had the springs in place with all that energy, it would be released immediately and the sample would blow up, right? And if you had the springs out of there, the sample would just crush in a very nonviolent way. And over the years, I've borrowed that device many times from Joe, in fact, I think a couple of times, because it was just such a perfect device to be able to show miners why you're designing pillars the way that you did. And I've been sitting in a room like this with all these kind of hardened guys, you know, that go underground work every day, and I'd take that thing out and demonstrate it, and instantly they'd say, ah, okay, I understand what you're talking about. So he was very practical and had this knack of building things that just simply showed some concepts. And the only other thought I wanted to bring up that nobody else has talked about is when I came into that lab and I was, I don't know, 19 years old or something like that, these were the people that were working in that lab, and many of them, I think you know who they are, and many of them formed what was termed the Minnesota Mafia, and and most of them have become quite influential in the field of rock mechanics in their own right. And it was such an opportunity for me as a young person to sit and listen to the conversations, because everybody went down to the rock lab to talk. There was a coffee pot down there, and Dr. Lackabon was always at the center of it, although he didn't say much, but he was there. And for me, it was a way I really could learn some new things from all these people around just by listening. So being a fly on the wall. And I think he was instrumental in forming that, along with Charles and Steve and others, of forming that rock mechanics group and just being there as the conversation went on. So those are a couple of additional remembrances. When Joe asked me to give a short talk about some project of interest that I've been involved with in recent years, I was kind of not certain about what I should talk about, because I didn't really know what the group here, the makeup of the group was. And so I thought it might be of interest to you to pick a very practical kind of topic that had some fairly serious implications. And what I thought was interesting here was some of the concepts used to carry out the project I'm going to talk about were things that I certainly learned here at the university that were drilled into my head in undergraduate classes. And also some of the tools used were developed by people here at the university. So it really, for me, brings things right back around to the importance of this department, certainly in my life, but also in the mining industry as a whole. So what I thought I'd talk to you about today was it's a fairly simple thing, but I think it shows how you can use rock mechanics in an everyday environment. And that was some issues that we had in sinking a shaft at the Lucky Friday mine, which is in northern Idaho, and it's right past the Montana border here. And if you ever drive down Interstate 90 going towards Seattle, coming from Montana, you can't possibly miss the head frame. It sits right next to the freeway, and I believe it's the tallest structure between like Billings, Montana and Seattle, I think. And the Lucky Friday mine is going to turn 80 years old next year, and it's a deep silver, lead, zinc mine that's mining on vertical veins. And the mine is one of the richest silver mines in the U.S. It's also the deepest mine in the U.S. This shaft took the depth of the mine down to about 10,000 feet. And it's in It's in some interesting geology that I'll explain in a second. The mine uses a mining technique. I won't talk about it because I don't think I need to here, but it uses a mining method called underhand cut and fill stoping, which we instituted in the mine in about 1983, so it's still the same mining method. The veins are quite narrow. They're only about 3-4 meters in width, and they're vertical and of extent of approximately 2,500, 2,700 feet in length. And some of the engineering challenges that we have at that kind of depth is due to the in situ rock stresses, of course, are very high at that depth. The rock mass itself is relatively weak, which I'll show you, and it results in squeezing ground conditions. Probably more seriously is a problem with seismicity, primarily due to slip-on faults. So it's essentially earthquakes that are mining induced at that depth. And they can be fairly serious. And I'll point out in a minute, the portion of the mine called the Lucky Friday mine was actually closed in 1996, I think it was, after 2 4.2 Richter magnitude seismic events underground. And I've always told everybody that you can certainly tell you're alive when you're standing within about 200 or 300 feet of a 3 Richter magnitude seismic event, because it's a very frightening experience. And at any rate, this mine does have seismic issues, also ventilation demands. The rock temperature at the bottom of this shaft that I'm going to talk about now is, I believe, 158 degrees Fahrenheit. And so the rock temperature at that depth is quite high, and it requires refrigeration on a very large scale. Also, logistics and material handling become a real issue. What's called the Lucky Friday mine is actually in 2 parts. Mark Christensen, my friend here, worked with me one summer there back in 1974 when I met my lovely wife, Kathy, here. That's the old portion of the mine called the Lucky Friday, and it's accessed with a shaft that's 6,200 feet deep, and it was sunk in 1980 to 83, if I remember right. And that portion of the mine was where the seismicity problems were quite severe, and it was closed, the one portion that was closed down. But before it was closed down, the geologists at the mine thought that there was a good chance that beneath an old mine up here called the Gold Hunter mine that was mined in the 1920s through the 40s, that the extension of the vein must be there, although it had pinched out back in the 1940s, and they thought there was no more ore there. So they actually drove a 1-mile-long tunnel over to it, and lo and behold, they struck a vein called the 30 vein, which is actually quite rich. And that's where the current mine is right now, at the Gold Hunter portion of the mine. And what you're looking at here are just the infrastructure tunnels, or some of them that exist. And so what I'm going to talk about now is this shaft that was sunk here. It's called the number 4 winze. Winze is a mining term for a shaft that starts underground and ends underground rather than goes through to the ground surface. So just a bit about some of the issues at the mine. This slide shows something about the rock type, its structure, the stresses at the mine, and the failure modes that are observed. The rock mass, whereas the Lucky Friday mine was in a very brittle, hard quartzite that was where the stresses tended to cause rock bursting, which is explosive failure of the rock. When you cross over a boundary line between another sedimentary unit, you enter something called the Wallace Formation, which you see here, which is a heavily foliated argillite. And the rocks in that area are called part of the belt supergroup, and they're all Precambrian sedimentary rocks that have been tipped up vertically. And so you can drive from Missoula, Montana to Coeur d'Alene, Idaho, and you see nothing but successive sedimentary units with vertically oriented structure in them. And it's a very extensive rock unit, and the mine is still in these rock units to 10,000 feet in depth. But whereas the Lucky Friday was in that very brittle rock, the Gold Hunter portion of the mine is in this much weaker foliated argillite, and it creates some problems that I show here. First of all, depending on the orientation of the excavation, you can get extreme closures of the ground, of the rock mass due to the ground stresses. And here you can see a tunnel that was originally driven with vertical walls on, that has now closed into almost a keyhole shape from the essentially the buckling of these beds when the tunnel is driven parallel to them. If we drive the tunnel perpendicular to them, there's no problem. It behaves perfectly. We don't have any issues at all. So orientation of the excavation is very important. This shows what we see when we bore a raise or a shaft, a small diameter shaft through this material, what can happen. And that is that in those areas that are perpendicular to the foliation, we get this buckling failure with large deformations into the opening. And keep that in mind for what I'm going to talk about in a minute, because we were seeing similar things happening in the shaft. These are just give you some idea about the stresses, and they're about one and a half times the vertical stress, the major horizontal stress. The intact argillite has a strength of about 70 to 100 megapascals, a uniaxial compressive strength. So it's a moderately strong rock with intact, but the foliation controls all the behavior of the material. Now, why was this shaft sunk? This shows a three-dimensional projection of the Gold Hunter vein here with the spiral ramp development in the footwall of the vein. And the colors, just to let you know, the colors just represent the grade or the value of the ore body. The NSR stands for net smelter return. This is I think about from 2015, so those values have changed. But the mining at that time was currently at this level. The ore body's been mined out above, and there's a very large vertical extent of this ore body left. The silver veins in this Coeur d'Alene district are really extensive. In fact, in this case, we don't know what the depth of the mineralization is, but it's getting stronger as we go with depth. And I show a little picture here. I think it's difficult to see, but this is the face of one of the excavations along the vein, and the vein itself is about 4 to 5 meters wide, and the grade of that, just to show you what the motivation is for sinking this shaft, is about 97 ounces of silver and about 50% lead per ton of material. And in practical terms, that rock is so heavy from the lead that we can't pick up a whole load with a bucket on an LHD. We can't pick it up. It actually tilts the material over. It's so heavy. So we actually have to muck it up with smaller changes. So there's great motivation to be able to get down there, but the shaft that we currently have at the Lucky Friday mine only goes to 6,200 feet. And so the company took a chance and said, and this is not a large mining company, and they took a chance and said, well, let's sink a new shaft, which is shown here, that goes down to past the extent of what we know is in the ore body there. And it was the largest capital project ever in the company to sink that shaft. It's a very complex operation to sink a shaft. I'll show you a little bit in a second. But that's the motivation for why it was sunk. So it's called the number 4 shaft, and the hoist room is at the 4,900 level, which the Gold Hunter mine goes back underneath the mountain from where the old Lucky Friday mine was. So the level designation of 4,900 to the old mine meant 4,900 feet below ground surface. We're about another 1,000 feet below ground surface where the Gold Hunter is. So that's actually about 6,000 feet depth with the hoist room, which is shown here. And it's quite a large excavation. I believe, if I remember right, it's about 65 or 70 feet across, and the height of the thing is about 40 feet or something like that. And if you can imagine this hoist, which was being constructed at the time, we had to take that entire hoist underground through the existing shaft through a 6-foot by 6-foot hole. So we had to cut everything up and take it down through that little hole and reconstruct it back underground. It was quite an amazing project. And the hoist rope was the only thing we couldn't take down because the spool was too large. And so we drilled a 9-inch diameter hole from the ground surface to the 4,900 level, and we actually took the spool on the ground surface, ran the rope down and rewound it on another spool at depth. So it was quite a project. The shaft bottom is at 8,620 level, which is about 10,000 feet. That's where we ended up with it. And there are major shaft stations at these different levels for loading out ore. And we're right now using the 6,500 level is where the bottom of the mining is, which is about 7,500 feet depth. That's ore mining. And the construction started in 2009, and the last shaft round, the blast round, was taken in 2016, and it was fully functional in 2017. So it took about a year to build the framework, the steel framework inside the shaft for the hoisting compartments in it. And the total cost of the project was about $275 million. And it was sunk by a company called Cementation, which is a large construction contractor that specializes in shafts. This shows the top station directly beneath where this hoist is as they're constructing the rigging to get the shaft going. I thought I'd tell you just a little bit about shaft sinking so you'd understand more when we're talking about the problems that we had. In that, I've shown some pictures around the outside that sort of progress from here to here and then back down to here with respect to how the shaft is constructed. The picture on the upper left is what's called a galloway. It's a working decks that people work from, and it's looking up from the shaft bottom. And these are forms, concrete forms for pouring a liner behind the shaft. The bottom is drilled using what's called a shaft jumbo, which is lowered for the work decks, and it's got hydraulic drills on it to drill boreholes. The bottom is mucked up with what's called a clamshell mucker, and it's loaded into buckets and hauled out up through the work deck. To pour concrete in the shaft for the lining, concrete forms that are steel forms that are collapsible and break away. They're taken to the bottom of the shaft, and they're always suspended up from the bottom, and the concrete's poured behind. And to pour the concrete, that same 9-inch diameter hole that we drilled from ground surface, we lined it with a ceramic lining that was not connected to the rock mass. It's floating in the hole. And so you pour concrete from a mix truck down that borehole, and so it just drops by gravity 5,000 feet, and it goes into something called a remix at the bottom, and it gets remixed, and then we load it into small mixer trucks and haul it over to the shaft. So this shows the initial way that the liner is poured, and I'm telling you this so you can get a picture about what happens with how the shaft is lined. I'm showing here that we use a 12-inch thick concrete lining. It's a circular shaft, and that's very common in shafts of virtually any size. The purpose of that concrete lining is not to prevent movement in the ground, because it's carried about anywhere from 30 to 50 feet behind the bottom of the shaft, and that shaft will actually close, at least elastically, it'll close before you ever put the liner in. So the liner does not really sustain much load at all. It's really there to keep loose material from falling and to provide a smooth surface for ventilation, and also something that you can bolt to, the shaft guides to. So it's really it's not reinforced, and it's not meant to reinforce anything. So what's happened is, to pour that shaft lining, we drop something called a curb ring, which is what this is, to the bottom of the shaft, or just above the bottom of the shaft. And that's poured with a high early strength concrete to provide a basis to put the rest of the liner on. So once that thing sets, which is, you know, in a matter of a day, the concrete forms are dropped to the bottom on top of the curb ring, and the concrete is poured behind, and then shaft sinking restarts. So this is the whole process that goes on. And the shaft bottom is shot typically in about 6-foot height lengths with blast holes, okay? It's done in a wedge cut, so it shoots it up into the shaft and then settles down, and then it's mucked out of the bottom. So this process goes on, you know, day after day going down. So we knew pretty much that we were eventually going to run into some problems as that failure in that board raise showed. We eventually knew that we were going to have some kind of an issue occur, but of course, the important part is that the interior space of that shaft has to remain open and free and clear, both for hoisting and personnel, and also for ventilation purposes, because this is actually used for ventilating the mine. And so we just kept carrying the shaft down, assuming that eventually we were going to have some kind of an issue. And typically, for those of you who are into mining rock mechanics and things, this is a kind of ground support that we used. The finished diameter of the shaft is 18 feet, and the exterior would be typically probably more like 22 feet or something, because it's overbroken on the outside. And we used 1.8 meter split set or friction bolts on 1.5 meter centers with chain link mesh, and we carry that right to the bottom so that no loose material can fall down. And that purpose of that ground support, again, is not to prevent deformation. And I think it's common misunderstanding that when people support a tunnel or something, that they're actually arresting deformation in that tunnel. And that's really not, it's a fool's errand to try and stop movement at this kind of depth and these kind of conditions, because it's going to happen no matter what you put in there. And so it makes it a difficult proposition with a shaft like this, where you have deformation, because the alignment of those shaft guides is very important. And I can't remember, but just a few degrees off misalignment can cause the conveyance going up and down that shaft to bind in the shaft. And if that were moving, you'd have to be continuously readjusting those things, and it has to be done very accurately. And the conveyance, I think, for hauling rock out of the mine is going at about 21 or 2,200 feet per minute. And so it's going quite fast. For carrying people, it's more like about 1,200 or something like that feet per minute. So something barreling up there, hauling a 20-ton load, you can't have misalignment. And so it's very sensitive. So we first saw some problems cropping up at about the 6,500 level. So it started at 4,900. So that's about 1,600 feet of advance in the shaft. We started seeing some minor cracking in the lining of the shaft. And so what we did is we said, okay, let's beef up the ground support and see how long we can hold off issues. And it did work. We put in, as I mentioned there, different kinds of beefed up ground support. We put in extensometers to measure deformations every 15 meters along the length of the shaft to monitor how it was closing. And we found out that we actually did stop and arrest the deformations to an acceptable level at that point. But when we hit the 7,500 level, this cracking that was fairly benign got very serious, and we had vertical fracturing on the north and south walls of the shaft, and we had large deformations. This picture shows one of those vertical cracks where it was actually the concrete lining was folding over itself in that area. And we realized at that point that we couldn't arrest that with just simply adding more ground support. And so we actually eventually had to tear the about, I believe it was about 150 feet of this liner out, which was, you think that would be a fairly easy job, but it was not. It was not at all. We had to actually use concrete saws to saw the length of it, and then we had to actually blast the liner out from in place. And the ground was continuing to move, and so we said, well, what do we do now at this point? So I say back to the drawing board. The first question was, what's the mechanism for these large deformations and failure? And of course, we realized it was the foliation that was causing the problem, but we used a simple two-dimensional model that was developed by Peter Kundl here at the university called UDEC, where we actually modeled the foliation. And I show a blow-up down here of this. We had a very large model where we actually put in the joint surfaces that represent the foliation. It's a discontinuum model, so we actually looked at buckling of these layers as it occurred. And this diagram here shows a magnified plot of what actually happens with the circular liner in those areas on the north and south walls of the shaft where the foliation parallels the shaft wall. And you can see the similarity to the actual thing that we can see in the board raise example that I showed earlier. And the second question was, can we stabilize this by just adding more ground support, reinforcing the liner or anything like that? And we came to the conclusion that no, there wasn't a chance that could be done, at least maybe not in a temporary way, but not as a permanent thing, because we still had another, I don't remember what, to 9,000 feet or 10,000 feet depth. So we still had another 1,500 feet of shaft to sink, and the stresses get higher and higher with depth. And so we decided that, well, actually I used a concept that Charles drilled into my head many times during classes as an undergraduate student, and that is that you should design an excavation such that it is optimum for the stress field and the situation that you have. And that excavation, most people think a circular excavation should be the perfect shape in most cases, but of course it's not here. And so what I looked at was changing the shape of the excavation to an ellipse instead of a circular excavation. And that, just on the right-hand side, it shows if you run the same model with that elliptic shape excavation, where you actually, in my view, is if the shaft wants to do that, you might as well let it do it, by excavating it that way. And so from the modeling, it appeared that we could, just by doing some fairly simple changes in shape, that we could actually arrest the deformations and continue sinking the shaft. So we decided to go ahead and do that. And I had a lot of trouble with the shaft contractor because he'd never driven an excavation that wasn't circular in shape, and he didn't quite know exactly how to do it at the beginning. So we struggled for, I don't know, a month or so with trying to get the blasting right, because it's quite a confined blasting area. It's difficult to create an ellipse in a vertical excavation like that. Perhaps if you're in a horizontal excavation, it would be easier, but we finally got the hang of it, and we tried that out, and this shows you what it looks like looking up from the bottom of the shaft. And based on the numerical modeling, we determined that we'd probably only need about between 2 and 3 meters of additional excavation in that shape to arrest that deformation. So we went ahead and tried it, and we put a lot of instrumentation in the shaft here that I show here, monitoring deformations and strain and hoop stress in the liner to determine if we were actually getting what we wanted. And what we found out was that we got this kind of deformation response. We found out that it took about 2 weeks or so in that period for the deformations to equilibrate. And they were quite reasonable. The maximum deformations we were getting were right around 20 millimeters, which was something, and this is before the shaft liner is put in place. So by the time we put the liner in, it had actually pretty much come to equilibrium. And it's curiously, as I'll point out in a second, you notice that the anchor at the collar of the hole, which was installed right in the ellipse at its largest point, is actually less than the deformation meter in the hole. We thought the instrumentation was wrong at first, that there was some problem, but we kept getting the same response all the time. You can see how rapidly the displacements drop off with depth away from the corner of that ellipse. So we continued sinking the shaft. I think we installed nearly 100 of these extensometers all the way down, so we were monitoring it all the way to the bottom depth. And we finally came to the conclusion, this shows it with a circular instead of a circular arch instead of an ellipse, but that by the time that we put those extensometers in, these beds had already to some extent buckled and dilated. And the reason that the deformation was less at the collar was because by the time we put it in there, they'd already dilated, and the rest of the rock was moving toward it, so it sort of gently crushed took the dilation, or I mean, crushed those beds together up against the outside of the liner, and thus the deformations were actually less than they were at depth. So we continued sinking this, and we were able to finish the shaft to 10,000 feet bottom. The result was that this little incident cost about an additional $25 million to fix, but it was far, far less than having to abandon the shaft, which is a lot of people were afraid that we might have to do, or I actually stopped sinking it. We sunk it to the bottom, and I was even down there, I think, a few months ago, and this has been about almost 5 years now, and there's been no recurrence of fracturing in the shaft. We've continued to monitor the deformations, and they're all quite small. They've equilibrated, and we're able to use a conveyance all the way to the shaft bottom without any issues. So the moral of my story was one that was lesson from Dr. Fairhurst, was that when you're trying to design support for an excavation, the very first thing you should do is you should ask yourself, what is the ideal shape of the excavation with respect to the stress state and the geology and its orientations? First, do that first, and then worry about how I should design ground support to take care of loose material and things like that. And that was something that I definitely had drilled in my head here. So anyway, that is the end. This, by the way, is a view of the shaft in the Lucky Friday mine here looking toward the east. This is Montana. Over here, it's quite a beautiful area. And we'll leave it at that.
Thank you, Mark. We would normally take questions, but because of time, we'll move on. And Mark will be at the dedication, at the lab tour, refreshments, and you can ask questions then. Okay, as I said, we move on to the part one of the dedication, and I'll just take a few minutes to thank some key people. And the first is Faith and Dick Coleman. This department has been blessed with incredible alumni, dedicated, quite prosperous, and it was through a contribution from Faith and Dick that we started the remodeling. I was both thrilled when this came in and both terrified, because there was 50 years of rock mechanics research that was stored in that lab. So the cleanup was quite a challenge, but certainly was needed. Also, many of you, as well as others on Zoom and that weren't able to make it, contributed, and again, thank you so much. Okay, with that, it's indeed my honor to introduce our Dean, Moss Cave, Professor and Dean of the College of Science and Engineering. Since joining the Department of Electrical and Computer Engineering in 1975, Dean Cave has served in various leadership roles, including department head, associate dean, and I believe for the past 3.5 years, dean of the college. Dean Cave is highly respected, regarded for his research in signal processing, specifically in wireless communications. He is a fellow of IEEE, and he has received numerous professional awards. Please join me in welcoming Dean Moss Cave.
Well, good afternoon. Distinguished guests, alumni, colleagues, everybody. It is truly a pleasure to be joining you this evening for this very special occasion in the history of the Department of Civil, Environmental, and Geoengineering, and the very distinguished program in geoengineering and rock mechanics. It's wonderful to see so many of you here, and we're excited to have some of Dr. Lackabon's family and other esteemed alumni and friends with us on Zoom. So welcome again, and thank you for your support. Rock mechanics research at the University of Minnesota has led to innovations in many areas. We certainly heard some of it just a little while ago. These areas include drilling mechanics, hydraulic fracturing, and poromechanics, to name a few. A faculty member who participated in many of these works was Dr. W. David Lackabon, as we've already heard. Although he was rarely credited with authorship on papers and advising of students, he was a valued colleague and mentor to several generations of researchers. Again, we've heard that already. And we've also heard that Dr. Lackabon earned his PhD in 1947 from the School of Mines at the University of Minnesota. And as we have already heard, and I take great pride in that, his first degree was in electrical engineering. And then I wasn't aware of the contribution certainly to analog computers, but it did help, certainly. Steve, we missed it. The two of us were next to each other. We should have gotten together and somehow done something like that. He taught courses in mining and petroleum engineering, as you know, and collaborated on numerous projects from designing experimental apparatus to building novel experiments. As you have heard, students benefited from his guidance and wealth of experiences, as well as his training in safe laboratory practice. Again, we heard. He retired, of course, in 1972, but continued his role, as we know, as an official director of the Rock Mechanics Laboratory. Once again, we've heard already that the laboratory was renovated thanks to the generous lead gift from the Coleman Family Foundation at the direction of H. Richard and Faith Coleman. After earning his bachelor's degree in civil engineering, Dick and his wife, Faith, relocated to Pittsburgh, Kansas, where his engineering expertise was used to expand the family business, Miller's Professional Imaging. And of course, we are thrilled that Dick is joining us on Zoom. So thank you very much again. The company has grown to be the largest professional photographic imager in the US. In appreciation for his education, the Coleman Family Foundation supported the renovation of the Rock Mechanics Laboratory to ensure that students at the University of Minnesota continue to have first-rate facilities. We also gratefully acknowledge, and Joe showed a list of names, some of the names, the alumni, friends, and faculty whose generosity contributed to the success and enduring legacy of the laboratory. So thank you all so much.
Thank you, Mark. Okay, with that, we'll conclude. We'll move to the rock mechanics lab. That's room 375. So either elevator or stairs, one story down. So our coordinate system is positive down. We'll have a very brief ceremony for the dedication. And then there's lab tour. We have students talking to tell you about their research, refreshments, snacks, and yeah, enjoy yourself. So thank you for coming, and I'll meet you in 375.